Hello everybody. We are doing the very last lesson here. Now my goal is not to completely finish it, but I want to do like maybe 2 or 3 examples, there aren't many examples. So it should get us really close to the end. And then when we come back on Tuesday, we'll look at some of the more difficult versions of this 5.5 assignment. And I also want to get you up on the board. This one is really appropriate for board work. So I want you to do some of the easy 5.5 homework problems from WebAssign just to get a little familiar with it, so when you come to class it won't be really foreign. But there's a game plan. You might remember the way we did derivatives. At first we did derivatives by the limit theorem. That was harder. And then we found shortcut formulas. And then we found that there was some complex derivatives, like of a product of 2 functions, and we had to discover a formula to do those more difficult functions like product rule, quotient rule, and then the pinnacle was the chain rule, using the chain rule to do derivatives. That was the most complex kind of function that we did derivatives for. The problems we're going to do today in integration are sort of like the counterpart to the chain rule. And so they're more complex, of course, but we have a very, very powerful trick that is useful in solving these. The substitution rule, or a lot of times you'll hear me refer to it, and other teachers and books refer to it as U-Substitution. The U is just a new variable. So fundamental calculus got us a long ways. It helps us do integration, and integration has so many applications in the world of math and physics. It can do areas, it can do volumes, which we're not going to get to see that, but in 6.1 that's the first little glimpse at how integration can do volume. Physics, we talked a little bit about position function, acceleration, and velocity. All of those are related to integration. And other physical functions called work, where you can compute the work in a system. All of that can be done by integration and a lot more. So the fundamental theorem got us a long ways. And it's dependent on the antiderivative. Now below here, or in the middle of this page here, we have some functions that do not have antiderivatives. These guys just don't have an antiderivative. If you look at the little table of all the antiderivative formulas, nothing even close to these guys is on there. So we're going to introduce a new strategy to attack these harder problems, and the way we're going to attack them is we're going to introduce something new. The thing new is a new variable. So the problem is the complexities of the functions. And if we can change the function so that it's not complex or not as complex, then maybe we can do the integral. And so that's the basic guideline here. What we want to do is we want to take a hard expression and turn it into a simpler expression by moving something that's making the problem difficult. Now those 2 problems in the middle of the page there, this is pretty difficult here. I have a function inside of the square root, and I have a product. This one is similar. I have a function inside of the square root. That's a composition. So this technique is going to be useful many times when we see a function inside of a function. So this new variable, like I mentioned, will be u. And what we're going to do is find a good u and substitute it in, and hopefully make the problem nicer. And what I mean by nicer is turn it into something that we can use the fundamental theorem, where we can use and find an antiderivative. Okay, So let's take a look and do some exploration. Here is that first example. And I'm thinking, boy, that is a hard antiderivative. Now, in order to integrate, it has to be continuous. Okay, little thought process before we begin. It's continuous everywhere. Because we have an x squared inside, that's always positive, and plus 1, so we're always taking the square root of a positive number, and that makes it continuous everywhere. So we're good to go there. All right, another observation. B. If you look at the problem and look at the table of antiderivatives, we have no antiderivative for this problem. Okay, so that's a clue that, hey, we're going to have to pull out some big guns to get this guy taken care of. All right. Now, another hint in the strategies when you're observing the type of thing we're supposed to integrate is notice that there is a function inside another function. Okay, now U-substitution, this method we're going to use, is not only limited to functions inside of functions, but those are the basic ones that we're going to start off with. So it's quite helpful if you see that. And so here's the game plan. I'm hoping for an easier integral. Now, before we actually attack this problem with U-substitution, I need to review a couple of things with you. So we're going to put this on pause right now, and I'm going to scroll back to the blank page on the page before, and I want to just review a couple thoughts with you about indefinite integrals. So this is something you really have to be attentive to here. If you have an integral f of x dx, notice the function is in x and the differential is in x, and this is doable. We can do it. In general, I'm talking about in general, we can do it. We might have to work at getting the antiderivative, the big F, but there's an agreement between the function being in x and the differential being in x. Now, what about something like this one? The integral, I don't want that color, the integral of f of u dx. This one we can't do. It's not in a position for us to integrate because there's not an agreement between the function input, which is in terms of u, and the differential, which is in terms of x. It doesn't agree, so we cannot compute this function, this integral, the way it stands right now. A couple more. I'm going to go a little faster now. The integral of f of x du. Same problem. We can't integrate that one in this particular form right now. Same dilemma because the function is in terms of x, but the differential is in terms of u. So that's stuck. Here's another example. The integral of f of u du. Now, notice this one has the agreement. This one is doable. We can do that one. All right, so these two, this one has agreement between the function being in u and the differential du. This one has agreement with the function being in x and the differential being in x. We're going to encounter some more complicated things. They may be like products. Integrating g of x times f of u dx. Okay, now we have a problem. Most of it is in terms of x, but the differential and the other function does not agree. Most of it is x, but I've got this u function in there. This cannot be integrated in this particular condition, so we can't do that one. Now, there may be ways to change it around, and that's exactly what's going to happen today, is we're going to figure out how to fix it so it's all u and du, or all x and dx. And very similar to that one is the integral of f of x, oops, I've been doing g first, g of x, f of u du. So most of it is in terms of u and du, but still we can't integrate it because the whole thing has to be in terms of all u's, the functions about u and the differentials about du, or the functions about x and the differential is about dx. So when we do integration, we have to slow down and be patient and make sure that when we change stuff around, we've got these good ones. So we're always looking for all u's and du's or all x's and dx's. Okay, that's one little insight that I hope will help you. Here is another insight that we need to talk about. And that is a reminder of implicit differentiation. Implicit. Now, we used implicit differentiation a long time ago when we were dealing with equations that had more than one variable. We're not just differentiating a function of x, but there might be u's and x's and y's or whatever. So implicit differentiation was, here's an example, a simple one to warm us up. U equals x squared minus x. Now, we have a function of u in terms of x's. So if we differentiate in terms of x on both sides, well, that's the long way. I don't want to do the long way. We'll start out with the fast way. When we did the differential interpretation of the implicit differentiation and took the derivative, it would be the derivative of u equals the derivative of the x function to x minus 1 dx. That's the short way to do differentials. Now notice the differentials are separated, and that's going to be really important for integration, because if we're integrating, this one, du, fits with this problem, and the dx fits with that problem. So those are things we're going to have to pay attention to. Now there's a long way of doing this where you have dx and you put u inside there. This one is a little tedious though, I think. Equals dx, and we put x squared minus x in there, and then we differentiate that. Now on the left side we get du dx. On the right side, we're differentiating x's in terms of x's. So the chain rule isn't really engaging us too much here. We're just going to get 2x minus 1. And then you can multiply by the dx on both sides. And you've isolated the du differential again. So it's 2x minus 1 dx. Okay, so this is just a little warm-up, a simple version of implicit differentiation, but those are two things we needed to review a little bit here. We're going to use both of those concepts to help us solve this hard problem. Okay, so how does the U-substitution strategy work? You look for part of the problem that's making it extra complex. And the part that's making it extra complex is a function inside of a function. So my goal is to make this problem easier. And what I'm going to do is I'm going to take u and I'm going to set u equal to 1 plus x squared. Okay, now when I do the u, because I'm integrating, I also need to know about du. So I'm going to do that implicit differentiation thing. Du equals the derivative of 1 is 1. 0 plus derivative of x squared is 2x dx. That's the implicit differentiation going on there. All right, now here's my thoughts. I'm thinking, all right, let's take this part out. And this makes the integral change. Now I hope, I don't know for sure, but I hope the change is going to make things better. And it doesn't always make it better. Sometimes you have to be creative on what you choose to be your u quantity. Okay, now my question is, this makes u to the 1/2 power. That's easy to integrate. I can integrate that. But can I integrate this problem in general? No, because notice there's not an agreement here. I have x's and dx's, and I've got this u thing. So we're stuck so far. It's one of these problems right here. It's got some x's and some u's, and oops, it's this one. X's and u's and some dx's, or dx there. So this problem is still not quite resolved, but I'm seeing a little promise because it's slightly easier to look at and slightly easier to figure out a possible antiderivative. Now I'm going to continue to simplify here, and I'm thinking, let's organize this, reorganize it. We're going to do the square root of u, and I'm changing my factors into different order, times 2x dx. Now here's my problem. If I want this integration to get done, I have to find a replacement for 2x dx. And that means I need to substitute in something to get rid of the x's and leave me only u's. Now, it turns out, hey, look at this. 2x dx. That happens to equal du. So I can do another substitution. This yellow part down here, I can take this out and do a second substitution for the 2x dx. It's going to be the integral of u, square root of u, times du. Now, with this little tricky technique of taking a u and substituting it in and changing the equation around, the function around, I have an integral that is quite easy to do. I'm going to integrate u to the 1/2 power du. And that's a power function, so we're going to get the 1/2 power goes up by 1. We're going to have u to the 1/2 plus 1. And we're going to divide by that new coefficient, 1/2 plus 1. You wouldn't have to write that down. You might be able to jump right to the answer. But that's 1/2 plus 1 is 3/2 times by that reciprocal. We're going to get 2/3 u to the 3/2 power plus c. We got the integral done. However, the original problem was an x function, and we have a u answer. But because we switched to u, the integration was easy. Now we can take our answer that's in u and switch it back to x. So this will equal 2/3, 3/2 power plus c. And I'm going to take the u out and put the x's back in. 1 plus x squared. I'm taking that u and plugging it in there. And this is the answer to that integral. Now, the original problem, there was no way we were going to figure out antiderivatives there. But by picking this nice u and figuring out du, the problem kind of collapsed into something very easy. We got something really easy here. That's the big idea for doing U-substitution. Okay, now I'm going to write down several things And I'm going to write them all down at once, and then you can pause and put these on your notes. But I want to look back here and figure out, what did we have, why did it work, and how can we come up with a plan to use this on a regular basis when we have hard integrals. So get ready to take notes. You may need to pause after I write everything down. Okay, so here's the big guidelines that we kind of drew out of that one example. It was a hard integral, and we didn't have an immediate antiderivative. If that's the case, this is a time when you should consider doing U-substitution. All right, so hard integral, no antiderivative, consider doing U-substitution. Now, it doesn't always work, but it's a pretty powerful tool, and it works a lot. When you guys go to Calculus 2, you're going to be using U-substitution all the time. Another indicator was it had this function inside of a function. Now that doesn't, that's going to happen a lot, and U-substitution is going to get us out of that jam. But U-substitution can also do other similar integration where you don't have functions inside of functions. So that's where we're going to be creative with the U-substitution technique. Notice how we treated du and dx as differentials. It's almost like we're using them as independent variables. Du is like its own variable, and dx is like its own variable. Okay, after we plugged in u, we had some leftover x's. That happened back here. We plugged in u and we had some x stuff left over, and we were stuck. We couldn't do anything with that problem until all the x stuff was gone. We had to get rid of the 2x and the dx. And fortunately, it worked because we had an easy replacement for the leftover x factors and the leftover dx. All right, so that's another strategy that you want to keep in mind. So sometimes you can't get the leftovers out. The x and the dx, you can't get them all out. That happens occasionally, and it might mean that you need a different u. So you'd have to go back and get creative and try finding out a different u. But that's the game plan. That's what we're going to practice here. And let's do a couple of these integrals. Now on the next page here, the substitution rule, or a lot of mathematicians call it U-substitution. It's kind of like the chain rule. Notice there is the function inside, and then outside we're multiplying by the derivative of the inside. That is the chain rule, except we're not differentiating. We're doing the chain rule backwards in a sense. And it works when we set u equal to gx. When we do that, we have a u here instead. That becomes f of u. And then there is a chain rule thing going on because we're changing the problem from x's to u's. So what is du? Du is the differential if we have u equal g of x. How do we differentiate that? That's the chain rule. We're going to get u du equals g prime of x, and then we're going to take the derivative of x, which is dx. That's the chain rule idea, and that replaces this part over here. And we can substitute out those extra x's and dx's, and we get an easy integral of f of u du. Okay, so let's take a look at number one. I'm seeing a product, x cubed times cosine. We've never integrated anything like that before. We've integrated cosine alone. We've integrated x cubed alone, but we have a product now. And worse than that, inside of the cosine is this extra function. So we have no antiderivatives here. Okay, so let's see, what should we do? Well, it's hard in this form. And I could make it easier if I temporarily set u equal to that inside junk, x to the fourth plus 2. And so that will change this problem a little bit. I'm going to reorganize it as well. Okay, now integral of cosine of u, that's easy. That's sine of u. That's easy. We transformed something there to where it's getting, could be easy. However, I still have some extra x factors left over. I have the x cubed left over and the dx left over. And can I do this integral right now? No, can't do it. Because there's not an agreement. I have u's and x's. U's and x's and dx's. It's not something we can integrate in this condition. So we got to continue the transformation and see if we can get a little more headway on this problem. And what we need is a representative for dx to substitute out. And if we come back here and do implicit differentiation, du is going to equal 4x cubed dx. Okay, now I'm looking right here and seeing, here's my problem. X cubed dx. They have to come out, and I have to put in u's and or du's to replace that. And I'm looking over at my du number here. Hey, look at the du. Du has x cubed dx. Now, I do have something extra here, though. The du has a 4 factor in it. So here's where we're going to get a little bit creative. What I need is x cubed dx. I need to find a replacement for that. And so this expression has the x cubed dx. So if I isolate that, I'm going to have a substitution. And I'm going to isolate that by dividing by 4 on both sides. So I will be getting, I'm going to write it as a coefficient 1/4 du equals x cubed dx. Now, I have the exact thing that's left over as a replacement. X cubed dx, it equals this guy right here. So I can do another substitution. The integral of cosine of u, take x cubed dx out and plug in 1/4 du. Now, honestly, I wouldn't write it down that way because 1/4 is just a coefficient. I would have skipped that step and just written 1/4 integral cosine of u du. Wow. This tricky thing of doing the substitution just changed this extremely hard problem into a way easier problem. So here we go. We can do this integral now. This has an easy antiderivative. It's going to equal 1/4 sine of u plus c. Integration's done. A hard problem became a very easy integral. Now we have just one little cleanup thing here to deal with. It's not an x function answer, and the original problem was an x function. So let's put it back into a function of x. 1/4 sine of u. I'm going to take the u out and put in my x is x to the 4th power plus 2 plus c. There's the integral. We just found the indefinite integral of a very hard function. All right, let's try another one. Okay, now the integral of x, e to the x, scratch work over here, integral e to the x equals itself. Okay, but this is not that. This is the integral of e to the 5x. It is not e to the 5x. It's way more complicated than that. Not too much more complicated, but this is got a function. 5x is a function inside the exponent. So we are dealing with a function 5x inside the exponential function. This is a candidate for U-substitution. Let's give it a shot. All right, so I'm thinking this does not have an antiderivative, because the only formula for antiderivative, this has to be a single function, a single variable, not a 5x variable, but an x or a u. The integral of, oh, by the way, the integral of e to the u is easy. It's e to the u. It's itself, because we have a single variable there. That's what the antiderivative tells us we can work with. So that suggests to me that why don't we set u equal to that 5x part. And then my integral will get better, because I will be able to say, oh, this equals e to the u dx. Okay, so can we integrate now? E to the u equals itself, the integral of no, we can't. We can't do this. How come? We can't, because the u's and the x's are not in agreement. We're integrating in terms of a u function with a dx differential. So we're not completely done. Once we find and plug in the u, we also have to find a way to plug in du. And that means getting rid of that dx. So here's what I got to work on. What can I plug in for dx? Well, if we go back to u, let's find du, and hopefully du will give me a resolution to what I can plug in. So I take the derivative of u, I get du. Take the derivative of 5x, we're going to get 5 dx. And there it is. There is a replacement, a relationship for dx that will allow me to substitute out dx and put in du's. But it's not a perfect replacement, because I have this extra factor of 5. I need to get dx isolated, because that's the last thing I have to get out is just the dx. And isolating that is really easy. I'm going to just multiply 1/5 on both sides. 1/5 times 5 is 1 dx. There it is. Dx is isolated, which means I can make this a swap, a substitution in for that remaining x stuff. So we're going to get the integral of e to the u, take dx out, substitute in 1/5. I'm just going to throw the factor, the coefficient out front, du. We just changed a hard integral into an easy integral. Now granted, that one's not as hard as number 1 was, but a lot of students get tripped up by something like number 2, because it seems like it's easy when it's not, because it had a function inside of a function. But the integration is easy now. We turn this hard problem into an easy problem. 1/5, the integral of e to the u is itself, plus c, don't forget c on these indefinite integrals. And lastly, let's convert it into what it's supposed to be, an x function result, 1/5 e to the, I guess I'll use red, 5x plus c. There it is. We've got the integration all done. Now, I forgot to talk about checking this. How can you check these, number 1 and number 2? Well, that's where the fundamental theorem comes in. Because if you integrate a function, you get a result, you could take the derivative of that result and it should take you back to your original function. Now, I'm not going to take time to do that, but you can check on a test. You can just do the derivative and see if it brings you back to the original problem. Now, you're going to be doing the derivative on that guy, and it's going to need the chain rule, say the same as this one. You can check by doing the derivative. And it's going to need the chain rule to differentiate it, but it should bring you back to the original function. Last one. Now, we're looking at an example here. Tangent. There is no antiderivative for tangent. So I'm making a couple of observations here. All right, just wrote a couple notes here, like what's going on? First thing we notice, there's no antiderivative, no inner function. So now it's like brainstorm here a little bit. What can we do with tangent? Well, because it's a trig function, fortunately, there is other things we can try. we can use identities like sine of x over cosine x dx. Now that's changed the problem into something new. I don't know if it's easier or not. It still doesn't have an antiderivative. So, okay, what could we possibly try? Well, let's try the substitution. And I see, okay, what are my choices here? All right, I'm going to take a shot in the dark here. Let's just get something started. Let's do u equal to sine x. And while I'm at it, I'm going to get my du, which derivative of sine is cosine x dx. And I know in the end, I'm probably going to need to isolate the dx so I can substitute that in here because I have dx. It's got to come out also. So I'm going to do one little extra step here and divide by cosine on both sides. And that gives me dx isolated, du over cosine x equals dx. All right, I want to try all of this here and see if I can get some good substitution going on to make this problem easier. So I have the integral of sine comes out. So I'm going to have u in the numerator. Now I still have the cosine in the denominator. And I still have dx. Okay, now I can't do this integral. This one can't be done because I don't have agreement. It's got u's and x's, so I'm not ready to go. The dx has got to come out. Now watch carefully, be careful here. I do have a substitute for dx. Dx equals this. I can replace dx, so that integral will become u on top. The cosine x is still there. And then dx, that I'm taking dx out and I'm putting in du over cosine x. Okay, now I have du and I have a u, but I have another problem. I have u du, that's easy, but I have cosine x squared. This is not working. I still can't do it. So I got the u's in and I got the du's in, but I did not get rid of all the x's. In fact, I made it worse. Cosine x squared, I cannot integrate this with the u's and the du's. So this looks like a dead end here. Shoot, well, let's try another option, because what would happen if we tried u equals cosine x? Okay, so let's find du while we're at it. Derivative of cosine is minus sine x dx. And, let's just see what happens so far here. I'm going to start setting up the integral. The sine x is on top. I've got, I'll make it black. I've got u on the bottom, and I have dx still on the side. Oh, wait. Look at that. Sine x dx. Sine x dx. So I'll rearrange it a little bit here so we give you an easier to see. 1 over u sine x dx. That algebra expression, sine x dx, I need to get it out. And I have almost a perfect substitution for it. There's an extra negative, though. That's not a part of the problem, but that's easy to fix. So if I multiply the negative on both sides, I will have negative du equals sine x dx. Got a perfect substitution there I can plug in here. So this will become the integral of 1 over u du times the negative. I'm just going to throw the negative out. Hey, that's an easy antiderivative. That's the natural log. So we can do this problem. This is going to equal the integral. So we're going to take the cosine out and put in a u. And we're going to take the sine x dx and put in a negative du. And that is a nice antiderivative. I have to multiply everything by negative, but du over u is the natural log. So this will equal negative natural log of the value of u plus c. And we can convert that back into an x function, negative natural log, absolute value of u, and u is cosine x plus c. So we got a solution to the antiderivative. It was an easy antiderivative after we found the right u. Now the moral of that story is sometimes when you have a more complicated function, the u isn't obvious and you kind of have to play around with it. And the more practice you get into these, the more insight you'll have at picking the right u the first time. But it doesn't always happen on those harder problems. I'm noticing one more thing. I'm noticing a log property here. The negative x and the negative coefficient with the log property, I can pull that onto the cosine and use that exponent. The negative of cosine, negative 1 power of cosine is natural log of secant of x. Slightly cleaner outcome. Also a good solution. So both of those are right. Anyways, we made a great start on 5.5. I want you to do your WebAssign homework tonight. Practice some of these. On next class Tuesday, I plan to be better and we'll do some of these problems on the board. This U-substitution is very, very important for those of you going on to Calc 2. You're going to use U-substitution so often in that class. So I encourage you to really plow into it, learn lots. See you in class. Bye-bye, everybody.